All right, so thanks. Appreciate being here. Yeah, I did my undergrad in physics, so I feel like I can hang at a physics conference. But then again, you know, I didn't get my PhD in it either. But hopefully, what we've been doing is going to be really helpful to you guys in the future. So, what is really a hyperscale data center? And that's the kind of stuff that I've been working on a lot. And I want to set this up for you guys in the scientific community in particular. Hyperscale really means massive scale, like tens of thousands, hundreds of thousands, millions of machines. So way beyond the scale of something like Blue Gene or kind of the supercomputers you think of. And they're running lots of diverse and fast-changing workloads. So the way I like to describe this is hyperscale is like, well, if you have a bunch of money and you want to start a rental car business, you could buy a few Ferraris, and that'd be cool. That's kind of like the high-performance computing machines. Or you could go perhaps even too far the other direction and buy a whole lot of cars that nobody actually really wants. And I joke that these are ARM clusters, but people get mad at me for that. So what we're really looking at in a hyperscale data center is something in the middle, like your reasonable little Ford Focus. And the only thing is, what I've been tasked with doing is taking that and just making it, a little bit cooler with accelerators. So there's a lot of different applications. This is just a sampling of some of the Microsoft ones that we run ourselves kind of in our first-party cloud, not to mention all the ones that everybody else runs on our, on our platform, on Azure. That's really the core of cloud and IoT. But we had a big problem. And the NVIDIA talk, they showed this off too, where you're saying, well, Dennard scaling ended. And the biggest thing to us that meant is, well, single-threaded performance started to fall off. A while ago, if we wanted to have twice the number of Xbox users, twice the number of Skype users, something like that, we could just wait a couple of years, and the CPUs would basically give it to us for free. Now that's started to drop off at a pretty precipitous rate, which means if we want to double the number of Xbox users, we basically have to buy not quite double, but about 83% more machines. It means we're just going to keep buying more and more hardware every time we want to get somebody on a new service. And if we want to improve the service, if we want to give you better graphics on Xbox, that means we're buying more hardware again. That's not a fun position to be in. So you've seen actually a pretty big difference. And what I want to show here is this is for Azure. But it wasn't that long ago that this cloud thing really barely existed. Back in 2010, we had 100,000 compute instances and things. By 2017, we've got millions. There's exabytes of storage, like petabytes of data storage all over the place. This has been a ramp up that's been absolutely enormous and has happened, happened just in the last like 7-ish years. I mean, I graduated from UW in 2009, which doesn't seem that long ago, and the cloud basically didn't exist then. And now it's something that's absolutely insane. And keep in mind that these are data centers. These are enormous multi-building, gigantic things that are out there that we're building all over the place. They're hundreds of megawatts in terms of the amount of power that they're burning, and that turns into $100 million+ just to power the servers. It's not counting the air conditioning and all that other stuff that's out there. These are absolutely enormous machines. So I wanted to compare this to something, especially for the HPC crowd, about, well, how does this compare to the world's largest supercomputers? So these are the top 4 right now on the supercomputer list. And the biggest one they have is about 40,000 machines. The next ones are 16,000 with some GPUs, so they get some extra performance there. But a single data center, just one of these data centers is usually 50,000, 100,000, sometimes even more machines. So one data center is bigger than the world's biggest supercomputer. And why is that really important? Well, data centers have been scaling. This is Microsoft alone. We're not even the biggest one. Amazon's bigger. In 2013, that was the distribution of our data centers. In 2014, we added a bunch more. 2015, 2016. And I haven't updated this yet for 2017. We've been growing at 100% a year for the past 5 years in a row. So we're basically just like sprinkling new supercomputers all over the globe, like pretty much every month or so. So here's the graph, the exact same graph that they were using. Basically came down to, the number of transistors is actually still going up, which is why you hear people say Moore's law is still not dead. It's just everything those transistors used to give us has fallen off a cliff. So the trick here is that, well, if we're getting more transistors, we just haven't been able to turn that into performance. What we need to do is be more efficient with the transistors that we're getting. We actually need to get performance from those additional transistors and not burn any more power. The thing is, we've actually known how to do this for a long time. Microprocessors, your standard CPUs, are amongst some of the least efficient ways to do any computation. If you think about it, when they're trying to add a number, not only are they adding a number, but they're caching all this data around it. They're prefetching things. They're branch predicting the next few branches. They're doing a whole bunch of stuff that's not related to the actual operation you're trying to do. If you specialize that hardware to do just the operation you want, you're not only a little more efficient, you're 10x, 100x, 1,000x, even 10,000x more efficient if you make custom hardware for whatever computation you're doing. So there's a lot of different options there if you want to make custom silicon. CPUs are kind of the most general, but the least efficient, and then custom ASICs are the most efficient, but the least general, because if anything changes, your ASIC's not going to work. There's many core CPUs and things where they just stamp out a bunch more CPU cores. There's structured ASICs, which are a little less. And then there's this big area in the middle. GPUs are probably something that most of you are pretty familiar with. And they more or less actually are many core CPUs with a whole bunch of cores and giant floating point units attached to them. But that's nice because it makes the programming model easier. Basically, CUDA can make it look an awful lot like C. But there's this nice thing here called FPGAs, which definitely feel and are programmed more like ASICs, so it's much more of a hardware kind of land. But they can offer efficiencies that are at least as good and sometimes better than GPUs in a lot of cases. So if we look back at that graph of efficiencies for different silicon architectures, sure, ASICs are going to be on the top right. CPUs are on the bottom left. There's a big space in the middle where we can do things with things like FPGAs. So I think, have most of you heard of FPGAs? You know what those are? Yeah, it seems like a fair number, but FPGA stands for Field Programmable Gate Array. And it's basically, the way I like to describe this is it's like silicon Legos. It's like if you want to build a circuit, if you want to build a processor for computing on on n-body simulations, you can build that. So if you want to build a boat, you can build it out of Legos, and it's not going to be the prettiest boat. But if you need an airplane, then just tear apart your boat and build an airplane. Whereas if you just built a custom boat, that boat might have been nice, but if you now need an airplane, you're out of luck. So that's pretty much what we have here, and you can change the hardware anytime. Many times, even it takes under a second to reconfigure these things to new circuits. So you have lots of options to constantly kind of reconfigure these, but they look like ASICs in terms of their compute efficiency. There's actually FPGAs in a lot of different applications already, and I think most of what you find is in the data acquisition. You'll find because there's lots and lots of I/O in FPGAs, and so basically you do lots of filtering, like the MOF correlator. There's NWA, the square kilometer array, Casper. CERN uses a bunch of these. Those are the Roach boards and the B2. So FPGAs are already actually in a lot of physics areas. It's just not in the core compute that I think a lot of people are usually used to seeing them. So here's kind of what the physical layout of an FPGA is. You can see it's just this really regular array of basic generic logic, and you use that logic to create whatever you want. And so you can create things like your PCI Express engine to get to your CPUs, your DRAM controller, your network controllers, and then all of that stuff in the middle is free for you to make whatever kind of computing elements you want. So customize both the processing logic and the I/O. So you may think for a data center, well, why don't we just use GPUs? That seems to have worked really well in physics and in other kind of high-performance computing applications. And what I loved is actually I looked up GPU server, and this is the one that popped up. It's actually smoking, which kind of made me laugh. But that's because these actually burn an awful lot of power. So they're burning 225, 300 watts apiece. that's as much, if not more, than the actual servers we have. So kind of like going back to that analogy with the cars, these are kind of Ferraris. Their gas mileage is just way too bad for us to be able to deploy on a big scale. That doesn't mean we don't deploy these in the thousands or tens of thousands, but certainly not in the millions like we have for servers at Microsoft. So the idea is more to optimize for the entire fleet, the entire hyperscale fleet, instead of just one kind of application. The other reason is, well, why even have this middle ground? Why don't you just make an ASIC out of everything? And so kind of graph here, the problem with making an ASIC is when you make a custom IC, if something about the algorithm changes or something about your data changes, you now have an expensive paperweight instead of a good compute engine. So if you look at what kind of stuff goes on in the cloud, the applications aren't very stable. They change a lot. If you look at how much machine learning has changed over the last few years, it's been incredible. And there's not one application running in all the cloud. There's all kinds of things running. That's the exact opposite that you want if you're making ASICs. So my favorite analogy for this is, how would you make an ASIC for Pokemon Go? That thing came out of nowhere. It was a huge cloud workload, took tons and tons of servers. And then just as quickly as it appeared, it disappeared. So well, it hasn't disappeared. I saw it like a week ago. There were people like running down the street and with multiple cell phones. I don't really know why that. Whatever. So the thing is, there's a nice migration of stuff, and I think this really applies to a lot of your scientific applications. Is when you're first starting out, you want to keep it in software because you want to be agile and kind of adapt to the data. But as your software gets more and more mature, the FPGAs give you a way to get some stuff onto your custom circuitry, and you can gently kind of migrate your code on there. And then once it's on there, it's actually not that big a jump to make it an ASIC if you really want to do that. And so it kind of gives you this nice gradual migration into there. And so when I first started looking at, well, let's put FPGAs in the data center, I took kind of what the HPC approach is, which basically made a card that looked like a GPU. And so it's this big honking card that had 6 FPGAs, and it's like a big pile of Legos in one card. But the problem is, that doesn't actually work that well for the data center, because this is what a standard data center server looks like. So you've got your hard drives. This is where the SSDs go. Your 2 CPUs, your network interface card. That was all the space they gave me for an accelerator card. And it turns out that this is the direction of airflow. So that CPU heats up the air. That one does too. By the time the air gets to the FPGA, it's 70 degrees C. So if your cooling air is 70 degrees C, you're definitely not going to put a 300-watt device in the back of that server. You're going to be melting everything behind it. So unfortunately, it's nice, but that's a tiny little pile of Legos. So there's not that much you can build. If you ever get one of those in your stocking, there's like 12 Legos to it. Not too many designs you can make. So what we wanted to do is network these together. And we went through a few iterations of this. But the current one is what we call a bump in the wire. So this is Catapult V2, and these are the boards. And what's basically going on with that is you have your CPUs and you have your normal network interface card. But instead of the network card talking to the network, it actually talks to the FPGA first, and then the FPGA can talk to the network. So both the CPU can talk to an FPGA like a normal accelerator, like a GPU, and it can get all of the network traffic that's coming to it and do things with your network traffic. So why does this matter? If your CPU, via your PCI Express interface, if you want to look at your application and say, okay, this function I'm going to move over to the FPGA, I'll write RTL code for that, you can do that and talk to the FPGA with a PCI Express interface. If you have things that are more like network acceleration, where you're like, well, I want to look at all these network packets and then do some kind of transformation or something on that, then you can do that kind of processing. The other thing that's really powerful is that these FPGAs are now connected to each other at hyperscale. So all of these FPGAs can talk to each other at very, very low latencies without ever going through the CPU, without ever going through any of the software stack that usually slows networks down. So if you look at how this works, a data center is connecting 100,000 plus, maybe 200,000 machines together. If they're connected in the same switch, they're only 2.8 microseconds away from each other, round-trip latency. If you're connected with a couple of switches, maybe 7 microseconds. But even all throughout the data center, this can be like multiple buildings and multiple areas in a region, you're still only talking 16 to 20 microseconds. So you can get to hundreds of thousands of FPGAs in 20 microseconds. That's like having one enormous kind of global FPGA. So you don't have to worry about what fits on a single device. You just put them all across. The other thing that's interesting is part of the reason that clouds haven't worked that well for HPC workloads in the past is a lot of times you're like, well, I need a lower latency network. I need special network processing. Not only is this basically the latency of InfiniBand and other specialized networks, but you can actually add your own computing directly in the network. So say you're doing like n-body simulations and something. When you have all these nodes, a lot of times you're basically saying, OK, who are my neighbors? Do I need to do anything based on this? And the answer for 99% of your queries will be no. But that doesn't stop the network traffic from having to go out. You go through the TCP or UDP network stack. It takes forever. It interrupts the CPU to say it has a network packet, and the answer is no. The thing is, you can put that kind of processing directly in the FPGA, so it'll pick up the packet, look at it, and go no. Pick up the packet, and then finally say, oh, OK, this one looks promising. Hand it off to the CPU. You'll get enormous speed-ups from that kind of processing in your high-performance computing workloads. So basically, even though one FPGA is just a couple of Legos, by the time you pile those all together in a rack and in a data center, you've got a pretty good big pile of Legos. And when you look at that data center map, how quickly that set of data centers is growing, you've got an even more enormous one. We're now deployed across 15 countries, 5 continents. Actually, I need to update that because we're in South Africa now, so we have 6 continents. Don't think we're getting to Antarctica anytime soon, but these FPGAs are literally in every single server that Microsoft's bought since 2015. So not only is this like something that has potential, they're out there right now, ready for people to use. So that's like this world's most enormous pile of Legos, which I absolutely love that kid's reaction. It's like, I'd be the same way. So what are we doing with this exactly? Well, the first thing we did was Bing, which is our search engine. So basically, it's like Google. Actually, if you ask Siri a question on your phone, that's also Bing. Or if you go to Yahoo, that's Bing. Turns out Apple hates Google more than they hate us. So the cool thing is when you see latency spikes like that, if you go to a search engine, you don't care if your query is handled faster on average than it usually is, but you do care a lot if it's not handled quickly at all. And so basically, your user experience is determined by these spikes. And you start to think, oh, this thing's useless. Well, what we've been able to do is not only eliminate the spikes, but more than double the performance. So this meant that Bing could do all of their workload with the FPGAs with half the number of servers. That's a big reason why Intel actually spent $17 billion on the FPGA company that we used, because they didn't like the message of, Microsoft only needs to buy half the number of servers. But the cool thing is, what happened here is we had said we were more than 2x faster, but if you notice, that's not 2x. So what had actually happened is that the global load balancer that we have for our search engine, when we turned on the FPGAs, it noticed that our data center with the FPGAs was doing so much better than everything else, it started funneling more than 2 to 3 times the traffic to our data center that it had ever been funneled before, and we were still not getting any of these crazy latency spikes. So that was a pretty cool result. You can do a lot of things like data compression. There's all kinds of things. This is a fun area where it's a good example of something where you think it's a really stable algorithm, but it turns out data compression keeps changing all the time. So even if you make an ASIC for it, the chances are that algorithm's going to change a little bit, or somebody's going to find another tweak. And so that's why you don't have compression chips in your CPUs now, even though you feel like, I just use zip. It's like actually underneath the covers, that stuff changes all the time. And then the biggest one that we're doing is infrastructure acceleration, which is network acceleration. So basically, I can go into the details if you want about this, but it's more than a 10x reduction of latency for every single packet that you're sending. This is the kind of thing that I think can enable a lot more processing in the HPC space, because you're not spending time in the CPU's network stack sending stuff to each other. It's actually by far the fastest network in the cloud. Like I said, it's InfiniBand kind of latencies. Bandwidth is 40 gigabit now, 50 gigabit. We're going 100 gigabit soon. And the cool thing is it's actually free to customers. We give this stuff away. And the reason we can pull that off is we're not spending CPUs like doing network traffic. So we can take the CPUs that aren't now getting burned on doing network processing and sell them back to you. So it's kind of a nice touch to get for free. Although the one thing that, the reason why I didn't have a talk on Tuesday is I was down at Hot Chips and we were talking about artificial intelligence, and it just wouldn't be a talk anymore if you didn't have to mention AI. So here's a good example of a deep neural network doing image recognition. And this is on the full server. So this is 2 beefy enterprise-class Intel Xeon cores working on that image recognition task. And every time it changes means it recognizes what the image was. So that's a baby, that's a dog, that's a sailboat. So I'm going to show you what happens with just a single 25-watt FPGA. So not the servers at all. That's what it can do. So it's a 10x speed up at about 1/10 the power. So it's 100x more efficient on that kind of workload. So we actually got this guy, if any of you recognize him, that's Uncle Satya. He approves my expense reports. He's also the CEO of Microsoft. So he's really excited about this because he called it the first AI supercomputer in action. And the way that they wanted to show this off is the biggest corpus of text that we have as humans now is now Wikipedia. It's just an enormous body of text. And so what if we wanted to translate that via the kind of best translation deep learning algorithm that we have? Well, if we were to do it with CPUs, with just a CPU, it would take weeks to months to do. If you did it with just one FPGA, it came down to about 3 hours, 4 hours, which is good, but not crazy. But if you actually threw our whole data center at that, then you could do it in less than 1/10 of a second, which is faster than you can blink. You could translate the biggest corpus of text that humans have ever assembled to any other language faster than you can actually blink. The cool thing is that was also on really old silicon. And so the next generation has well more than 10x the processing capacity of what we did here. So the cool thing we were just announcing, literally yesterday at Hot Chips, is Project Brainwave. And so what we're doing with this is using these FPGAs to accelerate neural networks. And so basically you have your kind of normal DNN, CNTK, described network. And we take those layers of the network and map them onto the various FPGAs and then connect them together through the actual normal Ethernet network. So we have a compiler and a runtime. Basically what you do is you hand us your big network that you've trained, probably on the GPUs, because GPUs are still the best thing in the world for training. You hand those to us, and we basically will map it across all of these FPGAs in the data center. And depending on how big your network is, that can span a huge range. You can describe it in anything, so Caffe, CNTK, TensorFlow, whatever your favorite kind of model is. Just describe that, bring it, and then underneath we'll basically handle that mapping. So what's the trick to doing this well? So the conventional acceleration approach would be to leave your neural network model in DRAM, because there's lots of data, because there's lots of weights, lots of offsets. So you put them in the DRAM, and then when a request comes along, so when you get a new piece of data, you see a new pulsar, you see something like that, you'll send it to the FPGA. It will basically run through the network in its DRAM. It'll pull in all those values, do the computation, and then go on its way. The problem is, for a lot of things that don't have high compute to data ratios, so convolutional neural networks like the ones with image recognition and things, they have a higher compute to data ratio, but a lot of the newest ones in speech recognition or in just about any kind of normal learning that's not image processing, they don't have anywhere near that kind of compute compute to memory ratio. So basically what ends up happening is, the DRAM becomes the bottleneck. All that happens is you're streaming stuff from DRAM and putting it back in. This is also part of why GPUs do so well on some of these tasks, because they have the fastest memory controllers. So what we do is instead, we're not going to use DRAM at all. There's all this little distributed memory. There's tiny distributed memories in the FPGA all over the place. So what we do is map just a portion of that network onto the FPGA. Then when a request comes in, every single element, every transistor in that FPGA will basically work on that request all at the same time. And then, so when it arrives, the entire chip is working on that request. It's not sitting there waiting for DRAM, waiting to request DRAM and then do a computation. So of course, the question is, well, if that works, what happens if it doesn't fit on a single FPGA? And that's the joy of that network, this kind of massive network that we have, is we just map it to different FPGAs. So basically, at the time that you start your request, we blow that out to just thousands of FPGAs that never even have to go to external memory. So it's just blindingly fast, terabytes a second of memory bandwidth per FPGA. And we can operate on a single request. So we don't need to batch up a whole bunch of requests before we start working on them to get efficiency. Because if you're doing like a web search, you don't want to go to the web, click search, and then have it say, well, we're waiting for 199 other people to do a search before we start working on yours. And this kind of stuff means, especially in physics, if you guys are looking for data events and you want to keep processing stuff in real time as data is coming through, you don't want to wait for 200 pulsars to come through and then start processing on it necessarily, because that means you're recording all that data to make sure that you're efficient when you batch it. This you just run through one at a time, all the time, and you can still get huge efficiency. So, it's not actually floating point operations we're doing. So this is with the hardware that we have deployed, the Stratix 5. We're getting 1.4 to 2 tera operations per second on neural network loads. But the thing is, the new hardware, which we just announced, actually puts that to shame. So basically, at different levels of precision, we can get up to 90 tera operations per second per FPGA with these workloads. The thing is, with narrow precision, you don't actually get much of a difference in your overall accuracy either. So with a single FPGA, we can hit just insane levels, and we're going to have these things all over the place, all over the globe. It's not just going to be in one supercomputer or in one region. It's going to be all over. Just a little bit more detail, but basically these things are really, really fast. So kind of in conclusion, the cloud is larger and more powerful than even the world's largest supercomputers, and we're growing at an insane rate. The FPGA really enables huge increases in computing performance and efficiency, especially on deep neural nets like machine learning tasks, even ones that aren't just convolutional neural nets. And the network acceleration enables almost supercomputer-like network performance, even at the cloud scale. So with that, I'm happy to take any questions.
Thanks for it's on. Yes, thanks for a very nice talk. I had one question. So I'm sure you did this calculation, but commercially, does this work out? The FPGAs are not exactly cheap chips, and so I saw now for the Stratix 10, you get about 90 tera operations per second. Mm-hmm. If I remember correctly, on the NVIDIA, you get about 120 tera in in single precision. So how does that work out for you?
So we have, for our GPU workloads, not like we don't buy a lot of GPUs and put those out there, but we buy 2 orders of magnitude or more FPGAs. Also, in terms of pricing, in terms of cheap, obviously we're getting a pretty good deal. If you show up and when the physics projects show up, they're like, hey, we'd like 20 FPGAs. We show up, we're like, hey, we'd like 1 million, and we get a discount. No, they're not as nice to us, but no, they don't discount. They're already low prices, but if you act now.
I have a very naive question. How much efforts are needed to make running existing C++ program on FPGA?
So the nice thing, like with the network acceleration, you never have to write any code. You never have to write a line of RTL, because if your application wasn't dependent on the network, you wouldn't be on the cloud. But for Bing, we did have to go through and write, like, look at the Bing code, look at the C++, and write it in RTL. It was about 30,000 lines of kind of gnarly production C++ code, but 3 of us wrote it in about a year. So it's hard. It's difficult, but it's not impossible. But I would also say a lot of your biggest bang for the buck is going to be things like computing in the network, which is doing stuff you never would have done in the software before anyway. So it really depends a lot on exactly what your application looks like. But programming it is harder, a lot harder than normal C, or even CUDA.
So we have, I don't know, a couple 100,000 lines of C++ code. If we wanted to take advantage of this and if we want to do a proof of concept, what would be sort of the right thing for us to do? How would we get the expertise? How would we?
Right. So when it comes to some of these things, like especially when it comes to your machine learning workload, you're probably going to be writing that stuff in TensorFlow or CNTK or Caffe anyway. And so there's no actual difference because we handle all the translation of that kind of stuff under the covers. When it comes to kind of math libraries, if you use BLAST libraries and things like that, more or less the same kind of stuff applies. It's only if you want to do really, really custom stuff that you have to get into the Verilog. And then I think what you do there is go talk to your grad students who are working on Casper and who've been doing the MOF core later and those kind of things, and they've got the skills to write that kind of stuff. But it's going to be 1 out of 100 kind of even programming students that code the lowest level details of this stuff.
You mentioned that you built a custom network to interconnect all the FPGAs. Can you comment a bit more on that? Is it extremely similar to InfiniBand? Is it something you plan to make available commercially also outside Microsoft? Yeah, so part of why InfiniBand works so well and it's so low latency is because they've basically wiped away most of the software stack, and they make it really easy. We've basically done the exact same thing here, where the physical medium isn't that much different, and it's normal Ethernet. But especially because we know we're in the data center, like TCP is so ridiculously high overhead because that'll handle a request from my cell phone on bad Wi-Fi all the way back there. When 2 computers in the same data center are talking to each other, that's just massive overkill. And so InfiniBand basically took advantage of that, knowing it was point-to-point links and it was going to have certain performance behaviors. We can do almost all the same tricks here, except we can actually scale to like full Ethernet, like full network, data center network sizes, because we know how to characterize those. And so we actually have custom network protocols that your stuff gets translated to. So you just get it running faster, even though you didn't actually do anything special to write it. You just write like you would any other kind of TCP socket style workload.